Welcome back to Chapter 19, the Circulatory System, taking a look at the heart. This is part number 2. The main purpose of the lecture will be to take a look at the conduction system of the heart. In other words, we're going to take a look at the electrical currents that run through the individual cardiomyocytes and how they correlate with the systolic and diastolic motion of the organ, the contraction and the relaxation. Now, as a quick reminder, your myocardium, which is your middle layer of the heart wall, is composed of cardiac muscle. Cardiac muscle is composed of cardiomyocytes. These are going to be your individual heart cells. And when we take a look at those from a histology aspect, we see that the cells tend to have a central nucleus. They tend to be filled with glycogen, and they also tend to have a large amount of mitochondria. The cardiomyocytes, when they line up next to each other, will create a thickened border, which will often stain darker. These are going to be called your intercalated discs. Many of you have seen that term before, especially when we did the histology chapter in 2085. Now, within the intercalated discs, or the border points between those two cardiomyocytes, you will also be able to see interdigitating folds, which are infoldings within the cell membrane that will increase the surface area of contact between the two cells. You will also be able to see some mechanical and electrical junctions that will hold the cells together. If you give me a few seconds, we'll switch over to the next slide where we can explore the visual aspect of the cardiomyocytes a little bit more. I just want to mention one statement that's also listed on the PowerPoint, and it's a very important one. It says that the repair of damage of cardiac muscle is almost entirely by fibrosis. That's right. Cardiac muscle and the cells are not able to repair themselves after they've been exposed to trauma or any type of damage. Instead, what will happen is that fibrosis will be kind of used to plug up the injury. This, of course, can mean that it can interrupt the electrical current, which can mean that the heart can beat or function at a lower expectation than before the injury occurred. Here is the picture of the cardio muscles and the individual cells as promised. On the left-hand side, under A, you can see your histology of your cardiac muscle. You can see the muscle fibers, you can see the striations within the cells, and then also notice that the darker areas or the darker lines have been highlighted as intercalated discs. Once again, that's the meeting point between the cardiomyocytes, or the individual cells that make up cardiac muscle. Over on the right-hand side of the illustrations, under B, we can see an individual cardiomyocyte. Notice how there is lots and lots of mitochondria lined up all over the cell. Those are the orange organelles. The mitochondria, or the powerhouse of the cell, will be our main source for ATP production for the cardiomyocytes. You can also see the appearance of the central nucleus. And our final picture, labeled C at the bottom, shows the formation of the intercalated folds, which are basically allowing the surface area between the two cells to increase. You can also see the desmosomes, which are the mechanical connections between the two cells, and the gap junctions being labeled. Gap junctions allow for cytoplasmic content to be shared between two cells. This will come in handy because in a little bit we'll talk about the fact how your cardiomyocytes rely on an awful amount of sodium and calcium and potassium to regulate their contraction and relaxation cycles. So by having gap junctions, these ions can easily flow between the individual heart cells. A few final notations before we kind of take this up to a higher level of the electrical currents running through the heart. When you take a look at your cardiomyocytes, as I've mentioned to you before, lots and lots of mitochondria everywhere. On average, a cell will dedicate maybe 5% of its cytoplasm to housing mitochondria. Your cardiac cells can use up to 25% of their internal consistency. Because of this, we see that the cells are very effective in using aerobic respiration. Respiration is the process of converting energy from a glucose molecule into the chemical energy of an ATP molecules. And if you do aerobic respiration, that means that you use oxygen as your final electron acceptor, thereby increasing the efficiency of how many ATP molecules you can generate with each cycle. So by having lots of mitochondria, it makes it more effective at doing aerobic respiration. You're also going to notice that at the top it says that your cardiac muscle will be rich in myoglobin, which is a hemoglobin specifically for muscle. So this will allow you to attract over your oxygen molecules. It will also have lots and lots of glycogen, which is a sugar source, as I was mentioning previously. Because of all this, we see that cardiac muscle is pretty much fatigue resistant, meaning that it will never, or it will have very little opportunity to switch over to anaerobic respiration. This is an excellent idea because it guarantees that the heart will consistently pump throughout the entirety of our lifetime. Your cardiomyocytes are often also described as myogenic. And to be myogenic means that you can initiate your own action potential. Now, what we do see happening is that the heart cells have to coordinate their action potentials so that the heart overall will get excited at the same time, allowing for a very strong contraction force to be initiated. The stronger the contraction force, the more pressure the blood is exposed to, making it easier for the blood to be distributed throughout the entire body. So we need a nice, strong heartbeat. And the cells that are going to initiate this heartbeat, these are going to be called your pacemaker cells. The pacemaker cells will lead the pack of the rest of cardiomyocytes, and they will be the first to initiate their action potential or their electrical current, and the excitement of that will spread throughout the entire heart, activating the myocytes and allowing them to contract as we go literally from top to bottom, from atrium to ventricle. So your heart cells or your cardiomyocytes that are going to initiate this heartbeat are going to be located in the right atrium, and they're going to be collectively called your SA or your sinoatrium node. So remember, these are the cells that will initiate the heart rate because they're going to be the first one that go through an action potential, and they'll spread their excitement from that point forward. So it starts in the SA node, which sits in the right atrium, and as the signal starts to spread, the next node it will encounter will be your AV node. Your AV node stands for the atrioventricular node. It is located in the lower end of the right atrium, very close to the interatrial septum, and it will allow the action potentials to start spreading down the interventricular septum. As it goes across the interventricular septum, it will activate the AV bundles or your atrioventricular bundle, which is also called the bundle of His. This electrical current will go down the entire AV bundle until it reaches the apex of the heart. At that point, it will separate to the left and to the right, activating the subendothelium conducting networks, also known as the Purkinje fibers. This network will allow every single cardiomyocyte in the ventricle to be exposed to the action potential as well as get excited to generate its own. So take a look at this illustration, and remember our goal is to excite the entire cardiac muscle, all of the cardiomyocytes, because when we excite it, that means we're passing an electrical current to it. We're generating an action potential. When you do all that, the response of the heart will be to initiate its contraction or its systolic motion. So right over here on this illustration on the left-hand side, we see that we have numerical indicators. So let's start with number 1. It is the top part of the right atrium, and that is where you're going to encounter your SA node, your sinoatrium node. These pacemaker cells are the first ones to initiate an action potential, and they will spread their excitement. And as you can see, they went ahead and they drew orange arrows, just spreading that excitement, and it will continue to do so until it activates item number 3, which is our AV node. The AV node sits at the bottom end of the right atrium, very near the interatrial septum. And from there, the excitement will spread down the interventricular septum through the AV bundle, or the bundle of His. When it reaches the apex, we can see that we have 2 white arrows drawn, one to either side, and that's because it will then encounter number 5, which is called the subendocardial conducting network. It also goes by the Purkinje bundles. These bundles will spread across the entire length of the ventricles, exciting every single cardiomyocyte as they go from the apex towards the base of the heart, or I should say towards the top of the ventricle. Once you've completed the conduction system of the heart and you've excited it by spreading this action potential, this electrical current throughout the entire organ, the heart will react by going ahead and going through a systolic motion, which is basically meaning that it's going to contract. So if you look at the illustration right here and you see your beating heart, I hope that I've made it clear that the heart can beat because it's been exposed to that electrical current through the conduction system. Once the electrical current has passed, then the heart will be able to relax or go through its diastolic motion. And also what I want to point out is as we continue to talk about blood flow and heart beating, please keep in mind that even though you have the pulmonary circuit on the right and the systemic circuit on the left, both parts of the heart will react the same simultaneously. So that means, for instance, if I say to you that the atrium is contracting, it doesn't matter if I say the left or the right, because what happens on one side happens on both. If I tell you that the ventricles contract, that means that both of them are contracting, just because they work in unison with each other. Now, how do we then explain initiating a heartbeat? Well, we already know that the heartbeat is initiated by our SA node, which is our pacemaker node. And what we see happening is when these cells are in control and trigger the heart rate, they set what we like to call as our sinus rhythm, our normal heartbeat that's initiated by the pacemaker cells. And on average, this will give us a vagal tone of about 70 to 80 beats per minute. On average, the heart will beat every 0.8 seconds. So if we plug that into the calculator, we get a number around 75 beats per minute. I do want to let you know that your pacemaker will coordinate with your nervous system, and together they will decide what the vagal tone will be for the individual bodies. If you see that the heart will spontaneously fire off an action potential out of sequence from the conducting system, or it will initiate a heartbeat from another location besides the SA node, this is then called an ectopic foci, which basically means an extra heartbeat that's initiated elsewhere from your pacemaker cells. There are many ways to describe ectopic foci, but in this case, the way we're going to encounter it is the fact that oftentimes if it consistently happens, that usually means that your pacemaker node has some damage to it. Now, if your pacemaker or your SA node is not able to complete its function, then what we will see happening is that the initiating of the heartbeat will move down to the AV node. So the AV node will then become responsible for initiating the heartbeat and spreading this charge along the entire heart. The problem is that this will lower your heart rates per minute. So on your PowerPoint, you're going to notice that towards the bottom of the slide, it says you create a nodal rhythm if your SA node is damaged. So your pacemaker cells are not firing off consistently and initiating that heartbeat. Instead, the heart rate will then be set by your AV node. But we do see that the AV node will significantly lower your vagal tone to 40 to 50 beats per minute. Now, in case you're wondering, what happens if your AV node is also damaged? So if the SA node can no longer work, we give it to the AV node. If the AV node can no longer work, then we go over to our bundle of His. Remember the one that will run down the entire length of the interventricular septum? The problem with this is that it will significantly lower the heart rate to below 30 to 40 beats per minute. Unfortunately, that heart rate is too slow to have sufficient blood flow throughout the entire body. So at that point, the patient would be an excellent candidate for getting a pacemaker installed, an artificial way of initiating the heart rate. Now, part of the reason why your pacemaker works so fantastic is because those cardiomyocytes, those cells that are clustered together in that top part of your right atrium, they do not have a stable resting membrane potential. And because they don't have a stable resting membrane potential, that means that they're very easy to excite, which makes them excellent candidates for initiating that electrical current or that action potential. Now, I'm sure that you've encountered action potentials before. It basically means that you're going to go ahead and manipulate the charge of the membrane. So we're going to have to do our depolarization and eventually our repolarization step. So go ahead and take a look at the slide, and it says right here that the resting membrane potential is usually around -60 millivolts. And what we see happening is that the minute the SA node or the cardiomyocytes get anywhere near that voltage, we see that the sodium channels will open up and it will cause a massive inflow of sodium into the individual cardiomyocytes. The cardiomyocytes will respond by increasing their membrane voltage, meaning they become more positive, and this reaction is what we like to call a depolarization. So in depolarization, you increase the membrane voltage, you make it more positive, the cell is reacting to the excitement, and it's all due to a flow of sodium into the cell. Now, it also turns out that as you're depolarizing, there will come a time where you also allow calcium to be recruited into the cell. So on your notes, you're going to see it says when it reaches the threshold of -40 millivolts, then your voltage-gated calcium channels will also open in, allowing for even faster depolarization to occur. At a certain point, the depolarization will peak, the action potential will occur, and it will come time to kind of shut everything down and go back to our starting point. For that, we're going to have to do our repolarization, and repolarization means that I now allow for potassium to leave the cell. And as it's leaving the cell, it's making the membrane more quote-unquote negative, allowing it to drop back down to its resting membrane potential. Since your SA node does not have a resting membrane potential, what we see happening is the second it reaches down and is done repolarizing, it will go ahead and initiate another polarizing and action potential step. So here we have it in illustrated form. So go ahead and take a look at your chart. You're taking a look at the membrane voltage. That basically is the electrical current that runs through the membrane. And as you can see, I've labeled for you on the first item, depolarization versus repolarization, because I really just kind of want to make sure that I highlight the fact that if you increase the membrane voltage, you make it more positive, you get it all excited. It's because sodium and calcium have to flow into the cell. And as primarily the sodium flows into the cell, the membrane voltage increases, and what we see is that we go through depolarization. Eventually you'll peak, and at that point you have to reset yourself. You have to go back to your starting point. That will be your repolarization. Repolarization means that potassium has to flow out of the cell. And the whole time that you're getting excited, you're basically generating an action potential, and the cells will respond to that action potential by initiating a contraction. To continue the discussion about the electrical currents, go ahead and take a look at the illustration that's playing on the right-hand side of the screen. And what you're seeing is a dramatic slowdown, obviously, of the electrical current as it's initiated by the SA node, travels down the atrium to the AV node, through the interventricular septum for your bundle branches, and then up the ventricular walls to the Purkinje fibers. And what this little diagram is trying to show you is as your action potential is spreading and exciting the entire heart, you can see that the contraction follows. That is the response of the cells getting excited. They will contract. Once the action potential is gone, the cells will go ahead and repolarize and they will relax. On the text end part of the slide, it just highlights the fact that your SA node, your pacemaker nodes, will initiate the heartbeat, and it will take about 50 milliseconds for it to reach the AV nodes. From the AV nodes, the signal will slow down a little bit, and it will take about 100 milliseconds to reach down the interventricular septums, and part of it is due to the fact that the ventricles are larger, so it will take a little bit more time, obviously, to excite all those individual cells. Once it goes through the AV bundles, we do see that the signal will start to speed up a little bit more. And also, finally, we see that the ventricular systole, or contraction of the ventricle, will basically progress from the apex up. And the reason for that is if you're taking a look at the diagram, you're seeing how the bundle of hits gets all the way down to the apex before the Purkinje fibers bring it back upwards. So I can't say it enough, and I'm so sorry for those of you who are going to be saying it over and over again. I just want to make sure we understand that the electrical current or the action potential is what excites the cell. And as a result of this excitement, the individual cardiomyocytes will go ahead and do a systolic motion. They'll do a contraction. Once the excitement, the action potential is gone, then you repolarize, you reset, and the heart will go ahead and relax as a result. And this whole process of exciting the heart and getting it to contract on average occurs every 0.8 seconds. This is figure 19.14, and what this picture is trying to show you is it's trying to connect the action potential and the actual muscle contraction. So in green, what we see graphed out is the fact that we are increasing the membrane voltage of our cardiomyocytes, and we're increasing it, meaning that we're doing our depolarization process. This is steps 1, 2, and 3, and this is all due to the fact that sodium is flooding into the cell membrane, increasing the voltage, and obviously calcium will also help with this process. Now, at the same time that your action potential is being generated in steps 1, 2, 3, and partly 4, we see that the muscle will respond by contracting. So this is the upward chart of the red part of the graph, and notice how it's been labeled as myocardial contraction. So the heart will contract, do its systolic motion as the end result of the action potential passing through the cells. Now eventually the plateau will come to an end, and the plateau basically means that the sodium and the calcium channels will close off, and the potassium channels, this is number 5, will now go ahead and open up, and potassium will come flooding out of the cell. As potassium floods out of the cell, we notice that our green line goes down, the cell repolarizes, it becomes more negative, it goes back to its initial starting point, and the muscle cells, the myocardial cells, they respond by relaxing. So you need an action potential if you want to contract, and you need the action potential to go away if you want to relax. And this is the whole concept of an electrocardiogram, an ECG or an EKG, depending if you want to do the German spelling of electrocardiogram. This is a way that we can measure out the electrical currents that run through the heart chambers. And because we know that the electrical current is our action potential, and we know that it will follow up by the heart contracting and doing its systolic motion, we're able to kind of predict the chamber filling and releasing blood, contracting and relaxing based on what we see the electrical currents do on a sheet of paper. So on your little diagram on the right hand side, I went ahead and I boxed in a typical EKG. And within a typical EKG, you're going to have three areas that you need to look at. You're going to have your P wave, your QRS complex, and you're going to have your T wave. Those are the three main reflections or three main parts of an EKG. Now remember, when you look at your EKG, this is just showing you where the action potential or the electrical currents are happening. Because you know, based on our discussions, that your SA node, your sinoatrium node, is the one that initiates the action potential, we can then also safely say that when you look at the P wave, you look at the work of your SA node. So your SA node is the one that fired off. That's what's going to cause the initial rise in the P wave. And as it goes from the SA node, it will encounter the AV node, thereby allowing the entire atrium to become depolarized. In fact, the P wave is all about the atrium, getting the atrium excited so that eventually it can contract. Once the atrium is excited, then this excitement will move down the interventricular septum, up the ventricular wall, and it starts to excite the ventricles. This is going to be represented by our QRS complex. Notice how it's a much larger peak, and that's because the ventricles are larger, more cells to excite, more electrical current to pick up. As a result of the QRS complex, we know that the ventricle will go ahead and respond by doing its systolic motion or by contracting. Now, in case you're wondering, well, my atrium did the depolarization and my atrium will contract in the P wave, or at the end of the P wave, I should say. QRS is about the ventricle getting exciting, about the ventricle depolarizing and eventually contracting. What's happening with the atrium? Does it just stay contracted? No, the atrium will start to repolarize and it will start to relax, and it actually happens around the same time as the QRS complex forms. But because the atrium is so much smaller than the ventricle, that signal is hidden or masked, so you don't really pick it up. Instead, what you see is you switch over to the taller peak of the QRS complex, which is all about the ventricle. Now, once the ventricle has reached its action potential and it's done its depolarization, then we see that the last part of our EKG is going to be our T wave. The T wave will represent the repolarization of the ventricles, which means that it will quickly follow the relaxation of the ventricle or its diastolic motion. Here you have the main events in text. So the P wave, you want to know, that's where my SA node, my pacemaker, fires. That is where my atrium becomes depolarized. So that means the left and the right. And eventually after the P wave, that is then where you'll have your contraction. So you need to have your action potential first, i.e. the increase in your P wave, and then you'll have the systolic motion or the contraction of the atrium. After that, you'll have your QRS complex. Now, on your notes, I wrote down your QRS complex is when your ventricle starts to depolarize. The shape is different because the ventricle is so much larger. But also, you want to keep in mind that during the QRS complex, your atrium is also repolarizing, resetting itself, and going through its diastolic motion, its relaxation. The signal is simply masked because the atrium is smaller than the ventricle. Finally, you're going to have your T wave. Your T wave is all about ventricular repolarization and allowing the ventricle to go ahead and do its diastole, its relaxation. Now, I do want to emphasize something, which is that we are basically just covering the main parts of your EKG. On your exam, you will be asked about the events of the P, QRS, and T wave, and you need to be able to explain to me if it's depolarizing, repolarizing, which chamber, and which chamber will eventually contract or do its systolic motion versus which one will be in diastole or relaxation. You don't have to know all of the individual in-between points as long as you know the three main reflections. Here is just another illustration showing you how on the left-hand side you're spreading that electrical current and how that corresponds with your EKG waves that you're seeing. So you could see at the same time that I'm communicating with my pacemaker and sending it down over to my AV node, I'm going to notice that the P wave turns red. As it goes down the interventricular septum, up the ventricular walls, I'm going to notice that my QRS complex comes into play. And as everything kind of slows down towards the end, we see that the ventricle is repolarizing, no longer receiving an electrical current. We see that corresponding with the T wave. So this is just to kind of show you the conduction system on one end, how we can see it in an illustrated heart, and how we can see it on an EKG on the other side. This is figure 19.16. It's probably one of my favorite figures of the chapter because it takes the illustration that we saw on the previous slide and it basically puts it in a drawing format. And what you're going to end up noticing is if you start on the first box, you can see that the atrium is colored red because it's having a wave of depolarization. It's getting excited because that's where we know our SA node is, our pacemaker node is. And as it spreads throughout the atrium, we can see on the little insert that the P wave starts to get formed. And as you move down to box number 2, you see that it says atrium depolarization is complete, which means that the entire P wave has been drawn. And what does the atrium do now that depolarization has been completed? It goes ahead and it contracts. It does its systolic motion. Now, in figure number 3, or I should say in box number 3, notice how we now have two colors. We see that the atriums, after they have contracted, they will go ahead and do repolarization. So they're going to reset themselves. So that's now illustrated by green. And at the same time, the action potential and the wave of depolarization is making its way down the interventricular septum and going up the ventricular walls. So what we're seeing is that now we have the initiation of our QRS complex. And by the time you get to box number 4, you see that the entire ventricular section is red, meaning that we're almost towards the end of our QRS form. And we then see that the ventricle will start to go through systole, which is its contraction. And as we finally get to the last part, the T wave, this is in box 5 and 6, we see that the T wave starts to form at the same time that the ventricle is turning green, indicating repolarization. And as the result of this, we'll see that the ventricle will do its diastolic motion. So keep in mind that we always have to start with the atrium, get the atrium excited, get the atrium to contract, then go over to the ventricles, get the ventricle excited, get them to contract, and eventually everything will reset and relax itself. And we tend to do this every 0.8 seconds. So let's take a look at some EKGs, okay? So the top one right there, A, this one is sinus rhythm. This is the normal rhythm. So you can see your P, your QRS, and your T waves. You can also see a flat line between each of the cycles, that flat line is called the quiescent period. The quiescent period is a very short period. It lasts about 0.3 seconds, 0.4 seconds, where both the atriums and the ventricles are relaxed. It allows time for the heart to kind of refill with blood and generate enough pressure for it to go ahead and induce another action potential and another systolic and diastolic cycle. At the bottom part, figure B, what we see happen is ventricular fibrillation. Ventricular fibrillation is usually seen, for instance, when a patient is suffering from a heart attack. We see that since the cardiomyocytes are myogenic, they're still able to contract and generate an action potential by themselves, but they're not doing it in a coordinated format. So instead of seeing a P, a Q, or S, and a T, we just get a bunch of little lines up and down because the individual cells are beating without the pacemaker initiating the heartbeat. So it's kind of like every cell for itself. This is then often while they'll go and they'll grab a defibrillator. That's what the little insert picture is for. A defibrillator basically shocks the heart. It's like giving an electrical current to the cardiovascular system of the patient, and it allows the heart cells to stop, reset, and hopefully it allows the pacemaker to take over, initiate the heartbeat so that they can contract in unison to create a very strong systolic and diastolic motion. Here are two more examples of abnormal EKGs. The top one, figure D, is when a patient has heart block. Heart block usually means that you have a barrier that prevents the conducting system from going in order, meaning that you're not activating your sinoatrial node to your AV node to your His branches to your Purkinje bundles. Somewhere along the way, the signal is being blocked. Now, in this case, what you can see is that the patient consistently has the D wave showing up, which means that their pacemaker, their SA node, is working just fine. Most likely they're having an issue with their AV node because it seems like the QRS complex is not always showing up, which means that those cells are not getting a clear signal from the AV node for the action potential to spread down the interventricular septum and up the ventricular wall. The one at the bottom, E, this one is a PVC, a premature ventricular contraction. This is when you have a little extra heartbeat. Some people will say your heart will skip a little beat. We usually see this quite common when a patient is nervous. Sometimes if you have a little bit too much caffeine throughout the day, or if you took a little 6-hour energy shot, or you took a little Monster. For some people, for some of the drugs that they take, we feel that the heart is kind of racing a little quicker than normal, irregular. Those are your PVCs that are being generated. It is quite normal to have a PVC here or there, but if they are consistently there, even during times where you feel that you are relaxed and you're not stressing, usually that means that you might want to go visit your cardiologist because you might be suffering from arrhythmias, which are irregular heart rates. These are good indications if there is significant PVC action within your EKG. All right, I think this will end our part 2 lecture. So remember that you have your discussion sessions for chapter 19, and I really do encourage you to hop on and post lots of questions, lots of comments and concerns. I am always an email away, and I will see you in a little bit for part number 3, which will be the final part for chapter 19.